I'd like to welcome you to our May webinar here at Traverse PC on Coordinate Reference Systems Part 3. My name is John Belcom. I'm an LS. I work here at Traverse PC, and I'm happy to walk you through coordinate reference systems. They're a part of every survey I do, and they really simplify grid versus ground versus geodetic versus terrestrial. All that's kind of wrapped up in these coordinate reference systems. So it really is an important topic. Now, I know your time is valuable, so I appreciate you spending an hour with us here at Traverse BC. I'll do my very best to make it kind of interesting, and hopefully you'll walk away with some great information. Now, I want to talk to you real quickly about how the continuing education credits work. You noticed when you applied for this or signed up for this webinar, there's a request CEU certificate. And in the email that you got to sign up, there's a link then to actually request your CEU certificate. If you are a connection member, that's free of charge. If you're not a connection member, there is a charge for that. But there's information here on another web page on how that works. And one of the things we do to meet some of the state requirements is during the presentation, I'll be giving out a 3-digit code. And I want you to write that down as I present those, because when the webinar is done, you have 1 hour to turn in your CEU request, and you have to submit that 3-digit code that we gave during the webinar. So within 1 hour of the end of the webinar, turn in that code, and then we'll mail out those certificates over the next couple of days, and make sure you get credit for that. Okay. Let's go ahead and jump right in. We took a look in part 1 at sort of the general information involved in a coordinate reference system. Talked a lot about distance and direction types. And then in part 2, we took a look at working entirely in local grid, and then we took a look at working with one of these hybrid systems. I just want to cover that again real quickly in just a couple of minutes for you. We worked with this example here, and we talked a lot about coordinate reference systems, and we said it's really how Traverse BC relates ground distances and geodetic positions and distances with grid distances and positions. And today we're going to throw true bearing versus grid bearing in there as well. So we said these are all part of the coordinate reference system, and then we took a look at this local coordinate system, and we said, you know, Traverse PC can come and work just at the ground level here. We turned off the geodetic and the grid down here because we really can think of working just entirely in a local Cartesian coordinate system. We've done that for years, so we're all very familiar with that, but that doesn't relate geodetic positions as far as GPS or GNSS goes. So we went through an entire survey with that, and then we switched over to sort of this hybrid kind of system, and we said, you know, we could instead either pick a geodetic position or stay with a local position as well, and we can think about this CRS grid up here. And if we want to stay in local coordinates, we can use a calibration, and we showed that, to calibrate our GPS positions to our local grid. Okay, and again, we're just working in a Cartesian grid. Or if I have time today, I'll show it to you, but I'm guessing we probably won't. We could also just think in terms of a local grid or a Cartesian grid at state plane coordinates. And everything we do, we're going to do just in local grid computations, but if we're not moving too far away from this normal point, our errors are pretty small. And so we'll continue just to work in Cartesian coordinates, and those positions can go right back out to GPS, GNSS, Google Earth, whatever, with very little geodetic error in them. And then if you remember, we spent a little time, I think it was in the CRS Part 1, a little time talking about geodetic versus planar computations. And the fact that Traverse PC is just as comfortable doing geodesic computations, forward and reverse computations on the geoid, as it is doing planar computations either on a projected grid or a local grid. So we spent some time talking about distance type and direction type. And we're going to be back into those a little bit today as we pick up our case number 3. Okay, so let's drop out to our outline here again. Let me just check my notes and make sure I've kind of covered what I wanted to cover here first. In all these webinars, we've got a lot of ground to cover, so I do have you hold your questions to the end. And I think the internet's running a little faster now, but during all the shelter in place, it had really slowed down. So I've kind of kept my fingers crossed that the webinar will stream okay. We've done pretty well so far, so I think we'll do fine again today. Okay, so here's what we want to do. Last week we took a look at 2 cases, and we said for each of these cases, let's look at this list of items. So I'm going to do the same thing as we jump into our 3rd case, selecting a CRS, distance and direction types, all that. And we'll just take these one at a time. So let's go ahead and talk about this 3rd case, working entirely in geodetic data, and we're going to use a Plss survey. So let me go ahead and bring that up. This is a survey that the BLM did inside of Traverse PC. It's actually included with our sample surveys, so that's why I've chosen this one. You can actually open Traverse PC, open this survey from our sample surveys, and pick right up where I left off. So let's talk about this in sort of general terms and see if we can kind of get you outlined here. So PLSS is kind of interesting in that when the system was designed back in the 18th century, we said we're going to work with true bearings and ground distance. That's how it was legislated, and that's how the GLO and the BLM have been carrying that out ever since. And I don't want us to get hung up, if you don't do public land surveys, I don't want you to get hung up on that today, because the important thing is this is a survey that represents working on a state plane grid and ground distance. And that's the same for you whether you're using a state plane grid, a UTM grid, a low distortion grid. If you're using any kind of a projection inside of Traverse PC as part of your coordinate reference system. So you can just come down here and pick any one of these that you might be using. Okay, this applies. So I don't want you to get hung up on the fact that we're working with the public lands system here. I think it'll be kind of interesting for you because you'll get a chance to see how Traverse PC does geodetic computations as well. But we're going to be talking about these same things that we've been talking about in all of the other case studies. Okay, distance and direction type and COGO and reports and deliverables and all that sort of thing. So let's take a look at kind of what's involved with a public land survey, and then just jump in and start taking a look at these. So public land surveys say we're going to do everything in true bearing so that we can account for convergence. So as we change latitudes, we get more convergence as we go north. In the southern hemisphere, as we go south. So we're working with true meridians along the way. And then we've got these latitudinal arcs that we have to follow along where the latitudes is constant, but of course on a projected grid the coordinates are going to change. And I'm not going to go through that whole discussion that we did in CRS Part 1. You can go back and watch the video. We laid that all out running a grid line due west as far and compared that with running a true line, geodetic line true due west. And quite a difference there as you cover more distance. So that's kind of the constraints here. The other thing that the PLSS specifies is that primarily we tend to work at a project elevation, and that controls our combined factor for grid and elevation, and I'll cover that in detail here. So let's come over to our drawing that we used earlier, and let's just talk about this a minute. So what happens in geodetic surveys like this is that I've drawn two colors here, state plane discussion in red and this geodetic discussion in green here. Let's talk about the state plane here first. So I start out with a geodetic position, a latitude, longitude, and ellipsoid height. And Traverse PC is going to use our coordinate reference system, okay, to come down here and compute a state plane coordinate. So that's why I said state plane CRS. With public land survey system, we tend to work in state plane. You might work in low distortion grids for your county or your transportation corridor. You might work in UTM. The discussion is very, very similar with that. So the CRS says, I'm going to take this geodetic position, and from that I'm going to compute a grid position on whatever the projection is. In this case, it's NAD 83 Oregon South. And then from that, I'm going to use the combined factor to get up here to a coordinate or position on the ground. Okay. Then I'm going to do geodetic computations, and this is the part that's a little bit different with the PLSS because this is a true geodetic survey. You might have a coordinate kind of survey where you're just doing planar coordinates at ground versus planar coordinates at your projected grid. That's fine too. It's all determined by the distance and direction type that you pick. Everything else works the same. So in the geodetic computations, we're actually computing geodesics on the ellipsoid. So a forward computation using geodetics and a inverse between two positions, geodetic positions, using geodetics. Geodesic, by the way, is just the shortest distance between 2 points on the geoid. Just like a straight line would be the shortest distance between 2 points on a plane. So we speak in terms of geodesics instead of lines. And then, of course, what we're after here is that we go from the inverse of these 2 points on the grid that are related to two geodetic positions up to their corresponding true bearing and ground distance on the ground. And this is what we actually measured in the old GLO surveys. This is what we're measuring when we come back and do a dependent resurvey. If you're not doing PLSS surveys, this is what you measure on the ground. And you might have a grid bearing and a ground distance instead of a true bearing and a ground distance. So again, just don't want you to be hung up on the fact that it's a PLSS survey. Okay, so let's go ahead and take a look at this particular survey, and let's walk through these pieces. Let's start by selecting a CRS, and I'm going to jump right in then to selecting distance and direction types. So we come up to survey information. I'm going to select it out of the toolbar here, but you can also go to Tools, Survey Information, and Coordinate Reference System. Remember I said that we're okay working with state plane for the PLSS. In fact, that's really how it all comes together inside of Traverse PC. We do the PLSS via state plane projection. So I'm working in NAD 83, the 2011 epoch, and I'm in the Oregon South zone. So this is my horizontal datum. I really am not interested in a geoid for this, so I'm going to set this to none. So the assumption here then is that my geoid heights are the same as my mean sea level elevations. Okay, so there's no geoid separation here, and I'm good with that. I've picked my ellipse, and I've got that set up now for the CRS. And we've talked about how the CRS really takes care of all the details. So all I really need to do is pick a CRS, and now I've got everything covered between grid, ground, and geodetic. Now, the distance and direction type we had on our list there. Remember we said we come in for the project and we tell it what kind of distances I want to work with and what kind of directions I want to work with. And that really sets us up. So what I've done here, I've said I want to work with geodetic distance per the PLSS at project elevation. and I want to work with true bearings, and I want those to be computed using a mean course convergence. And again, we've labeled that as PLSS, so it makes it real easy to pick out which ones are the PLSS options here. And this is where you might choose something a little bit different. You might say, I just want to convert that projected grid to a local grid using a ground distance. Okay, I want to call this a ground distance, and that can also be at project elevation. What that's going to do, though, is that that's going to switch Traverse PC out of geodetic mode into planar mode. So that will tell Traverse PC, we're doing planar computations, but we're still going to equate a position on the ground or a distance on the ground with a position and a distance on the grid. Okay, and it's going to happen exactly the same way that the geodetic relationships work that I'm going to show you today. So I picked my distance and direction type. We're going to come in and talk about this compute average a little later, but I really have everything set up just the way I want, and I'm good to go. So that's all I need to do to get set up with this. Now let's jump in and kind of talk about the nuts and bolts of this, distance and direction areas. I'm going to open up the Traverses Manager, and I'm going to go into the format with the F9 key. And just for a moment, I'm going to turn on square feet. So here are the square feet computed for each of these parcels that are being drawn over here. And I'll go ahead and just zoom in on this section 1 here and hide section 3. So I'm using groups, and I'm just hiding this group so we're not looking at it. I'm just looking at the traverses in section 1 that represent these lots here. So the first thing I might do is I might come in and say, well, you know what? I do everything in acres as I'm working in aliquot parts. So let's come back and kind of set that up again like we did earlier and just reverse what we did. So I'm going to talk about displaying acres there instead. So now I've got the acres displayed, and per the BLM manual of instruction, these are acres on the ground. So even though I know I'm using a state plane projection to do all the computations, I don't even want to see a grid area down on that projected grid. I want to assume that everything I'm dealing with is ground areas, just like I'm dealing with ground distances. And that's really, really important. You know, remember the GLO actually issued the original patents, and they were all based on these aliquot parts that had these dimensions and this supposed area. So over all these years, we're staying true to that by considering ground distances and ground areas. So what I want to do is just open up one of these traverses here, and I'll go ahead and delineate it down here so you can kind of see which one, and that will allow me to just zoom in a little tighter here. Turn that delineation off, and let's just open this traverse up. And I see that Traverse PC is displaying true bearings and geodetic distance for me. Okay, remember that's what I set for the survey parameters. So when I created this traverse, or the person who created it did, Traverse PC copied those settings, and if we go into the view format and go to advanced, we're going to see here's those same settings here. Now the one thing I might change in this particular traverse is if I want to compare this with the GLO notes, I can easily then come in and tell Traverse PC that I want to see the chains here. And if I highlight one of those distances, it'll tell me the units are in chains at an elevation of 4,300 feet. So I've got a geodetic distance in chains at project elevation of 4,300 feet. And again, we've talked about this. The CRS is taking care of all that for me. So I really only just have to know that I'm dealing with ground distances here. Now, what if we change between grid distance and ground distance? And I'm going to go back and set us back to feet just so we can kind of see these a little more dramatically. So here's my ground distance in feet. Let's come back in now, and let's change this from PLSS ground distance to grid distance. So watch this 1338.48 for instance when I hit OK. 1338.07. Okay, so I'm about 4/10 shorter. And that makes sense because I'm basically showing you now what the chord is across a latitudinal arc. Remember that geodesic's not a straight line. It's the shortest distance between 2 points on the ellipsoid. So it's actually an elliptical arc. And this grid distance now is the long chord of that. So we expect that to be just a little bit shorter. And all of these distances changed. So that distance type really is doing the yeoman's work here of saying, okay, here's that geodetic distance converted to a ground distance based on this combined factor based on a project elevation of 4,300 feet. Remember I said there's lots of pieces, lots of components. The great thing is I just select the CRS and Traverse PC does the rest of it for me. So pretty sweet then that Traverse PC is taking care of that for me. Now if I want to see what all the components are, I think it'd be real interesting to come back here and go into the format. Watch what I'm going to do. I'm going to include Y and X, and I'll just throw on the theta here so you can see what that is. And let's expand this out a little bit. Okay, so for each of these points, I've got the northing and the easting. These are the grid coordinates. So these are the state plane coordinates, and they look like state plane coordinates. And I've got the latitude and longitude for the points. So those are the geodetic positions. And for each point, I know what the convergence is. So let's go back to our display here. And you can see that that traverse really put all three things here for me. Let's come back. So in this traverse, now the way I've got it formatted, I'm looking at the true bearing and geodetic distance. That's the true bearing and ground distance. So it's distance at the ground, but it's derived from the geoid. So Traverse PC calls that a geodetic distance versus a ground distance. I see the coordinates, northing and easting. Those are the Cartesian coordinates down here on my state plane grid. And I see the latitude and longitude. Those are the positions on the geoid here. Okay. So I get all three things kind of coming into play just by turning on those columns in this traverse view. And now you can kind of start to see how they all coordinate and sort of come together. And I wanted to turn this convergence on just so you can see not much difference, but as we move to the different corners on this 40-acre parcel here, I've got slightly different convergences because I have slightly different eastings on those. So pretty cool. Okay, when I did the webinar last month, one of the comments someone wrote back is, I really want to see ground area versus grid area. And what they were talking about, and I'm going to jump in and talk about that next year. What they were talking about is, remember I said the BLM doesn't want the area down here on the state plane grid because what was conveyed in the patent was so many acres for that aliquot part at the ground. I mean, they had no idea what a state plane coordinate grid was in 1800. Okay, so I'm really interested in area here at the ground, and all these distances that I've labeled on the drawing are all ground distances. And I want to show you that in the closure view. So let's go ahead and in this traverse open up the closure view. And again, I'll use the toolbar up here, but I could also say view. I could come down and say, I can remember where this is at. Here, closure view. F6, a lot of you guys just press F6 for the hotkey. I'm just used to using this toolbar up here. And let's take a look at the closure view and kind of talk about this in terms of the CRS and what we're after here. So right off the bat, the header shows us we're working with geodetic distance at project elevation 4,300 feet. So we're all based on geodetic computations, but we're working with distances at the project elevation of 4,300 feet. We're also displaying true bearings. Okay, so everything that's displayed in here, all this information, is going to be ground distances and true bearings. So if I see an error that's displayed, okay, or if I see a distance, total distance around here, that's ground distance. And this is what I'm primarily wanting to focus on right now, is that I've got 33.632 acres at the ground. And that's what we saw back here in the Traverse Manager when we turned on acres, 38.632. And if we labeled the acres in the drawing, we'd get 38.632 also. Okay, now, what if I come back to this traverse, and you saw me do this a moment ago, but what if I come back and I say, in addition to getting rid of all that stuff we don't need anymore, I'm going to go into the advanced, and I'm going to say, let's show me the grid distance instead. And remember, we saw these distances change, so we're going to see those change again. Here's my 3807. Let's come into our closure view and just refresh it now. 38.608. Oops. I remember I talked about in the first webinar, part 1, that the BLM Manual of Instruction in the 40s, 47, said since we're working in planar coordinates, we could do a compass rule adjustment on a lot like this, and that would account for what's called apparent misclosure. Apparent misclosure is the error I get if I do planar computations around this aliquot part. So they said, oh, we can do a compass rule adjustment and that'll get us close. The problem is that's all it did. It really only just got us close, and it was kind of a farcical way of coming up with what the area should have been. And I wanted to show you this because now I'm looking at grid distance, okay, and I've got this area that's wrong. I could do a ground distance based on planar computations, and I still wouldn't get the exact right area because I'm not accounting for the convergence properly of the east and west side of that part, okay, because they're different. So as soon as I come into the traverse and I tell it I'm working with geodetic distance at ground elevation, all my distances are right, okay, so I've got all the right information displayed for that traverse, and when I refresh my closure view, my areas are right. So again, the coordinate reference system just took care of the traverse for us, and now it's taking care of the acreages for that as well. So pretty sweet that I'm working where I want to, up here on the ground, in ground distance and true bearings for distances, bearings, and areas, all because of the coordinate reference system that I selected. And that's kind of the big takeaway from all that discussion that I want you to walk away with today, is that the coordinate reference system really is taking care of these things for us. So we just are picking the distance and direction type, and it's taking care pretty much of all distances, directions, and areas for us in the survey. So now I want to drop into drawings and drawing settings, and you're going to say, boy, this feels like deja vu to some extent. So let's take a look at this distance 1259.12. Here it is, 1259.12 in the traverse view, the distance between 108 and 109. And now you're seeing that I've got some point labels overlapping here, kind of ugly to read. But remember, before I plot this, I'm going to go into Layer Tools, Modify Layers, turn those off. So I'm not worried about some overlaps while I'm working on it and putting it together, because I'm going to turn those off later on. Now I certainly could come back in, turn that layer on that I just turned off, and simply drag these down so they're not in the way. And I'll do that. Okay, so let's talk about this drawing. I'm going to right click and go into Drawing Settings. I also could have gone up to Tools, Drawing Settings. And there are a number of tabs here. The Miscellaneous tab is the one I want us to open now. And look what we've got here. Distance type, direction type. And let's just talk about this a minute. Remember what I did here in the traverse view? I changed from geodetic distance or ground distance at project elevation to grid distance, and we saw those distances change. I can do the same thing here. I can say, I can select a grid distance and watch this 1259.12, 1258.73. Remember, we're about 4/10 shorter because now we're dealing with the chord instead of the arc. Okay, we can do the same thing with the bearing. So watch this 890804 when we switch to a grid bearing. 891157. Okay, so in this drawing, the coordinates control the endpoints of this line between 108 and 109, and those coordinates are state plane coordinates. So if I display grid distance and direction, I'm getting the planar inverses between those state plane coordinates. Simple. Okay, that's not what I want. What I want is to show ground distance and true bearing, and that's just what I did. Now I haven't changed the state plane coordinates. The state plane coordinates are still where they were when I displayed grid bearing and distance. But Traverse PC CRS is taking care of all of that for me. And you saw me do this also in the Traverse view. We could also say, hey, I'm going to compare this against the GLO nodes, which are in chains. So I want to display chains here. And I'm going to stop here just for a moment and say, you can have Traverse PC display distance units or not. Okay. These distance units it's displaying are actually found in the settings. So I can go into settings and units, and I can tell Traverse PC that if I'm in chains, I want to display, whatever the chains are, abbreviations. Okay, and that's the CHNs. If I'm in feet, I want to use whatever that abbreviation is. So in this drawing, when I went into drawing settings and told it to label the units, that's where it got that. But I can also override that, and I can say I want it to do CHS instead. Okay, or I want to do space CHS instead. So pretty slick as far as allowing me to identify what I'm actually displaying in the drawing. And I think this is really important. Our users in Texas, of course, choose Veras. Okay, one of the options in here, and then they can decide, do I want to just put a V there? Do I want to put VAR, or do I want to spell out Veras? Okay, they've got all that opportunity to do that just because of what's done here. If I don't put anything there, remember, it goes back to those program defaults. Okay, so I don't have to put something in for every drawing. So I want you to see real quickly here then that the drawing in Traverse PC is tied into the coordinate reference system just like the closure view was, just like the Traverse view was. And we're going to take a look at code reports and deliverables as we go here. We're going to see they're all tied in. But I wanted you to see the drawings here. So the other thing I want to show you real quickly with this, and let's just go ahead and OK this, and we're in PLSS distance and direction. I want to drop down to the bottom down here, and I want to show you how we use drawing variables. So I'm going to zoom in down here, and I'm going to add a text item. I'm in paper space, that's good enough. And I'll just put in something. Now I'm going to double click that, and I want to put in some information for this drawing. Typically I would put this in the drawing template so that every time I started a new drawing with that template it was available. But I want to tell whoever's looking at this drawing that I've got a coordinate reference system based on this datum. Well, I'm going to use the grid because it includes both, and I'm going to insert that. I want to tell them which distance type I'm using. So I've got a distance type. I want to insert that, and I want to tell them what direction type I'm using. So we're going to pull down the direction type and insert that. So now, without having to type it all in, anyone looking at this drawing knows that this is based on NED 83, the 2011 epoch. I'm in the Oregon South zone, number 3602. So The savvy person knows that I've got state plane at play here. But more importantly, I think, is the fact that I'm showing geodetic distance at project elevation and true bearings at mean course convergence. And both of those are the methods used for the public land survey system. So real neat way for me to have anyone who picks this drawing up anytime in the future track right through with me so they know exactly what we're doing. Now, Traverse PC is actually plotting state plane coordinates, or the coordinates of the CRS, or the CRS. So the drawing itself doesn't really care what the coordinates are. It just shows the distance and the direction and the area. And if we come back to our drawing we've been using, the drawing's up here at ground distance. And it's really, I guess the stuff down below here is really invisible in the drawing. Other than the fact we put the drawing variable in that said which state plane datum we were using, the drawing isn't displaying anything about the geodetics or the grid information down here. It's really just all about the true bearing and ground distance at the ground. Okay, and so I can plot this out, write a PDF of it, and the coordinates and the geodetics never come into play. I got exactly what I want. However, when I go to export this, I can export this as either grid coordinates or ground coordinates, and we're actually going to do some of that here in just a moment when we do the deliverables, and I want you to think in terms of the calibrations that we did earlier. So I can go Tools, Export Drawing As, and when I pick a CAD format, for instance, like an AutoCAD DWG, here's those calibrations. So the calibration equates two coordinate systems. So a calibration could just as easily equate a state plane coordinate system with a ground coordinate system. And I could export this drawing to CAD in ground coordinates if I wanted to. Okay, the great thing about calibrations is that it doesn't change any of the labels here. Okay, so the labels are still going to show ground distance and true bearing. It will shift some of the positions of the coordinates around a little bit because it has to, in essence, rotate, translate, scale those. Okay, so they are at ground. And we're going to talk about some ways to do that. But I just want you to, just for a moment, kind of hang out with this fact that the drawing is in CRS coordinates, and that might be how I want to keep it forever. And or it might be that I need to have another coordinate system represented by a drawing, and I can do that in Traverse PC. Okay, let you kind of just hang on that a minute, and let's drop into the next section here. So let's come in now and talk about COGO and kind of how this works inside of Traverse PC. If I come in and select 2 points here and go to random inverse, I'm going to do that from the Traverse view. The Traverse view says I'm going to set this dialog up to use the same distance type and direction type as the Traverse. So I see true bearing, geodetic distance. And here's 1338.48 for the distance. Here's north 0832 west for the bearing. So true bearing and geodetic distance. If I do a summary of this, Traverse PC is going to tell me that this is the random inverse. I'm showing geodetic distance and true bearing. And then I love this. I kind of come down and find out all the information about it. So I'm going from 109 to 115. I get the coordinates in the state plane grid. I get the latitude, longitude with convergence and the grid factor. Okay, so this isn't the combined factor including elevations. It's just the grid factor for the projection. And then it tells me what it computed. And just like I would expect, I expect for a geodetic computation to have the equivalent of a forward bearing, a backward bearing, and the two of those, because I've selected mean course convergence as my direction type, the two of those get averaged out for a true bearing. I have a geodetic distance at ground elevation of 4,300 feet, okay, and we give you the slope distance as well. And then here's that combined factor. So this line from point 109 to 115 has a mean elevation, and it has grid factors at both ends of the line, and that gives me the combined factor for that line. And then this dialog also includes some vertical information if I had that in here. And these are at the same elevation, the endpoints, so I don't have any difference there. So I want you to see that Traverse PC gives me a report, or we call it a summary, out of this COGO that tells me exactly what I'm working with. Now watch what I'm going to do. I'm going to expand this show options. Is this starting to look familiar to you? Distance, direction, and units. We see this all over the place in Traverse PC. I'm going to pick a grid distance, and Traverse PC just changed to a grid distance of 1338.07, 0.4 less. Remember, we've seen that before. And a grid bearing. So here's my grid bearing. And I'm basically off by the convergence, okay, that Traverse PC computed in the geodetics. So real straightforward for me to come back. And of course, now if I did a summary with this, Traverse PC would tell me grid distance, grid bearing, okay. I don't have a forward and reverse bearing anymore. I just have a bearing, okay. And I don't have a combined factor now because I'm doing grid distance. I'm down on the grid. So the factor on the grid is always 1.0. So pretty straightforward. I'm going to switch back to PLSS, and now I can work all day doing COGO at ground. Come back to our drawing again here. So that COGO dialog is set up to give me all the information at ground. You saw how I switched it so I could get all the information at the grid, and if we spend a few more minutes I could show you how I could get all the information on the geoid, the ellipsoid, okay? But what I've chosen is to leave it in the settings of the Traverse view, so I do true bearing and ground distance. And I'm going to do all my COGO this way in the survey. Again, the geodetics and the state plane are just means to an end. What I'm really interested in is everything at ground here. Okay, let's take a look at a report real quick. So next thing on our list here is take a look at reports, and then we'll jump into deliverables. So let's do a Traverse report on this. I think it's in here, Traverse report. Tell it what we want reported. Let's do the Traverse data. This all looks good. Hit the OK button. So just like we saw earlier, Traverse PC is going to tell us that for this Traverse report, I've got section 1, lot 1, geodetic distance, true bearing, just like we saw in the COGO. Here are my true bearings and geodetic distances that I showed in the Traverse view. Here's my error summary. Again, any error would be displayed in geodetic distance and true bearing. And here's that acreage, 38.632. Okay, so all the reports are reporting everything in ground distance, geodetic distance of project elevation, and true bearing, just like I would expect. So pretty nice that I don't, I'm not thinking about selecting these each time. I'm just letting the coordinate reference system kind of do that for me. If I go ahead and write a PDF of this, remember we said PDFs really don't care what coordinates are. It just writes it out. So let's go ahead and write it out. Here's my drawing, Traverse PC PDF. We'll print that out, overwrite the file that we created earlier. And now we can view it and fit to page and get our drawing. Okay, so easy enough for us to put that together. Let's talk about corner cards and creating corner cards for this. Lot tables. This user went ahead and typed in the areas, okay, for the different lots that they wanted to report on this, they could just as easily have come up and said, not that one, this one, I want to put in a lot table, okay? And Traverse PC would have given them all the options here, but I want you to see that acres are here, and if I created a lot table with acres, Traverse PC is going to look at the drawing settings, which are set to geodetic distance at project elevation and true bearing, and it will base the acres on that. Okay, so any relative error, linear error, lengths, all this information is going to be geodetic distance at project elevation and true bearings. So I'll get the areas that I want precisely because the lot table is tied to the coordinate reference system, just like the drawing is. Okay, I said corner cards. Let's produce some corner cards real quick, or a corner card real quick, just so we can kind of see how this works. I don't see any of that kind of computation here in this particular plat example of ours, so I'm just going to create these real quick. I'm going to add some points to a traverse, and I'm going to call it Southeast Accessories. I'll start at point 1000 for accessories, and this all looks just fine for me. So I'm going to start by picking an existing point. I don't have to be over the symbol. I can be over the end of a line, a label, whatever I want, and that adds point 109 to the traverse for me. And I'm just going to pick some arbitrary corners that I might have staked out here, or corners I might have tied for accessories, and I'll press enter when I'm all done. And let's just come in and clean this up a little bit. So here's my accessories. Let's go into the traverse for that, and I'm going to set it up so that these are side shots. Hit F10, and then I'll go into the side shot settings and turn on distance and direction for that. Yep, that'll give me what I want. And then I'm going to use this command here that says draw just this traverse. So Traverse PC comes in now and basically draws the start of my corner cards for me. So I can come in and tell Traverse PC I want to use a different scale. Well, 20 feet to the inch would work just fine. So let's use 20. Okay, move this over a little bit. And now everything that I've drawn in this drawing, okay, is set up just like I want. Okay, I could display chains if I wanted, right? If I want to change the units to chains, that's just fine. And now if I apply that, the units are chains instead of feet. But I've got geodetic distance at project elevation, 4,300 feet, and true bearings. So I've got exactly what I would want to have on a corner card for this. I've got a traverse to support it, and I've also then got a drawing ready to go. And of course, if I want, when I go to close this, I can save that as a drawing, and Traverse PC will hold that for me. Okay, it'll make a new drawing for me. I'll have a drawing for the corner cards, and I can do that for all the corners on there. But that's one of my deliverables, and Traverse PC just takes care of creating that for me with the proper CRS information. Okay, I'll close that out, come back and take a look. Let's turn that traverse off, and let's talk about exporting this out to Google Earth. I like to show that just because you can actually see what it's actually doing. So let's come in and tell Traverse PC we want to export this to a KMZ. We'll pick the settings we want. I'm going to tell it we're going to do, oh here, the tagged traverses. Traverse points are visible. That looks good. Everything else looks good. Let's go ahead and write that. And let's preview that. So the great thing about preview in Windows is that it just opens the application, and it's going to take us right there to where our survey was in Oregon. So here's that dependent resurvey. I can zoom in, and probably should hit R here just to see the plan view of it. Kind of see how things fit in there, where those sections were laid out. And looks like I've got pretty good fit with the lines of occupation that are already out there. Here's the section 1 over here. Pretty nice for me to kind of see how everything is set up. And I don't know if you know that it's nice, Traverse PC has information for each of these. So I have some information about the lots that are here. Kind of nice. And the points, I mean, all that has information with it. Yeah, kind of nice to have that available. Here's the line, all the line data. Okay. And so Traverse PC, in this case, used the geodetic positions that are part of that coordinate reference system for the survey and made it, sending it out to something like Google Earth, real simple. Well, imagine how easily then this would go out to your GPS or GNSS data and do for stakeout. Kind of pretty neat there. Let's go ahead and do the same thing with GIS. Let's write an Esri Shapefile. Now, this is kind of interesting. I don't want to write local coordinates, however I could, but it would be better for me to actually either write geographic, which is going to write out the latitude and longitude, or projected, which is going to write out the state plane coordinates, but it's going to include the projection information. So anyone reading this file could pick up that projection file and go, oh, this is NED 83, Oregon South, zone 3602, at a project elevation of 4,300 feet. I mean, they know all that information from the file that went out. Now, when it comes to CAD, we talked about that earlier. I could calibrate this to go to ground coordinates. I could also use this tools convert coordinates. But before I do this, I want to talk about something called average point and a project location. And we're going to use that when we export ASCII coordinates, and I'll move pretty quick here. So I had put this in as, you know, maybe kind of once we get through this, we want to talk about some grid to ground, average point, and best practices. And I want to pick it up here as we talk about exporting data for stakeout and the deliverables. And I'm going to show you the average point because that's kind of key to this. So I'm going to go into the survey information and project factors. And I can tell Traverse PC that, remember we had that survey that we looked at that we said it's the way Trimble has done it forever. And we do it that way in Traverse PC as well. This kind of hybrid coordinate system where we pick this one point that's normal, and then we expand or contract everything to or from that to go from grid to ground kind of thing. So that's what this is all about. And this location point is this one point here. Okay. So what I'm going to do, just for the fun of it, is I'm going to tell Traverse PC I want to compute an average. And just going to compute the location of this project that I can consider my average location. I'm going to tell it use all 21 tag traverses and go ahead and compute that. Now I'm going to just draw that on here and drag this drawing up and in and over here so you can kind of see what it did. So here's my average point, and it used all these points to compute that with the least squares. And what I'm really interested in is telling Traverse PC to use that as my project location. Okay, so now when I come back to my project factors, here's that average point it computed, and I could have labeled that. Okay, at that location and that average elevation, I have an elevation factor, a z factor of this value. At that location on my projection, I have a grid factor of this value. I can combine those and compute a combined factor. So that's how easy it is now for me to get that combined factor. And now when I go to convert this drawing and use the tools convert coordinates, I can tell Traverse PC that I want to convert the entire survey here, and I want to go from grid to ground, and I want to do that about that project location, average project location. So it brings in that average point. That's going to be my one normal point, and it's going to use this combined factor that it computed for me, okay? And it knows whether it's 1 over the combined factor or the combined factor over 1, depending on whether I'm going grid to ground or ground to grid. And I could simply convert these coordinates and then export it to CAD. Now I'd have to move some things around because the coordinates would shift, the points would shift because they have new coordinates, but I could clean that up and even save that as a separate survey to go out to CAD. Okay. Now, what about staking out terrestrial? Now, of course, if I'm going to export this to my GPS equipment, I already have latitude and longitude as part of my CRS. So I'm not going to do anything else. I'm just going to say File, Export, export the entire survey or those traverses. I'm going to go to ASCII, and I'm probably going to recall some format that I've already got set up, like Trimble Business Center State Plane, for instance. And it's going to write out latitude, longitude, description, that sort of thing. But if I want to export this out for terrestrial work, I'm going to come in and tell Traverse PC I want to use let's see what that one is. Okay, I'm going to use XYZ for my export, but I'm going to tell Traverse PC I want to convert coordinates. And I'm going to go into the settings and tell it how to do that. And I'm going to say I want to go from grid to ground just by picking what I want to do, and I want to use the project location. So it's got all this same information I just brought up in the tools, convert coordinates, and it's going to use that now when it exports those coordinates. So I'm going to say OK, give it some file name that I want to export to. It's going to send it out to a CSV file. I'll overwrite that, hit export. There's my coordinates. And look what happened here. I just love this. So Traverse PC is telling me that I'm converting grid to ground with this factor about this base point. Okay? Elevations are not converted for grid to ground, and then it tells me my base average location. So every point has a grid value, and it got converted to a ground value when it exported it. Remember, elevations don't change, but all the coordinates did. So now when I bring these coordinates into a data collector and go out in the field, these are ground, so the inverses between them are ground distance and ground. Really, I'm not interested in the direction so much as I am the angle between 2 points when I have a backside and a foresight. So that angle is based on the ground coordinates, not the grid coordinates. So everything's kind of taken care of for me when I export those, all by the coordinate reference system. So pretty nice. So let's come in and wrap this up. I'm not going to get to another case study today, which is just fine. So we're not going to talk anymore about site calibration, but you understand when I talked about the CAD file, I could easily calibrate that CAD file on export, and it would end up in ground coordinates versus state plane coordinates. Okay, so what I want to have you walk away with from this then today is that whether I'm talking about the public land survey system or whether I'm working with a low distortion projection for my county, or whether I'm just working with straight UTM or state plane projections, Traverse PC really, with this coordinate reference system, is taking care of everything from either ground to grid or geodetic to grid, and everything from grid back up to ground, so that I can actually be working on the ground up here with ground distances and ground directions and ground angles, even though all my computations are either done down here on the projected grid or on the geodetic geoid. So pretty sweet that the coordinate reference system is taking care of all that for me, And you saw how it was really no work for me to do the COGO that I wanted to have the drawing come out the way I wanted to generate reports, to send out my deliverables, to do my export for stakeout, and then of course the real sweet calibrations that Traverse PC does allows me to coordinate this CRS with all kinds of stuff. And all of that happens once I've set it up without me hardly even thinking about it. It's pretty nice. Okay, I hope I kept that interesting for you. I hope it was kind of interesting to kind of walk through some of these pieces, and I hope you got something out of today's webinar. Thank you again for joining us.